This meeting is being recorded.
Welcome everyone to this week's CDAC webinar. It's a pleasure to introduce Fatima Safari from Adam Mickiewicz University in Poznan. Fatima is a chemist who's interested in materials in extreme conditions, crystallography, and organometallic systems. She has a master's from Sharif University of Technology in Iran and has just completed her PhD thesis working under the supervision of Andrei Kotrusiak in Poznan, as you can see. Fatima has done a number of studies under pressure of organic systems, many at the ESRF, where she spent quite a bit of time in the last few years. And today she's going to be telling us about some of her most recent work on stabilization of organic molecules by rational doping. So welcome very much to our webinar series. We're looking forward to your talk.
Thank you so much, Professor, for your invitation and also introduction. Yes, today I want to talk about our new idea, actually, about stabilizing high-pressure polymorph at the ambient condition. But let me talk at the beginning about some challenge in high pressure, because despite the huge facility which we can use in our field, but still we have a lot of challenge, which when we want to describe our result for other fields in physics or in chemistry, they say, okay, so how we can use it at 10 gigapascal? I mean, how normal people can use it and what is the application for it? So I think after more than 60 years, which people can use diamond anvil cell, we should also add to our goal for all our projects to try recover or stabilize our new phase or high pressure phase, because I think this is one of the most important way to keep high pressure or material under extreme condition alive at the future. So in my work and this story, I started by resorcinol. Let me talk and give you some background about this important compound, because resorcinol is one of the first organic compound which the phenomenon of the polymorphism was described by it. And at the 1936, the phase alpha, and 2 or 3 years later, phase beta was observed by the Robertson. But also around 50 years and 40 years later, the high pressure researcher started to work on it. One of the important thing about the resorcinol, because it has a huge application in pharmaceutical industry, in organic compound, and also in synthesize. And another thing that resorcinol is a little bit different with another drug, because we can use it directly for the treatment. So that is a reason there are even a lot of books only about the resorcinol. But you can see how is the structure of resorcinol, which this small molecule has only 2 hydroxyl group, which changing the position of hydrogen in hydroxyl group can generate different properties, physical and chemical properties for this compound. And the alpha phase of this compound has an anti-anti position of hydroxyl group, but another phase is anti-syn. But I should mention it that syn position in hydroxyl group up to till now only reported in the co-crystal, not in the pure pure polymorph of resorcinol. So as I said, there is long story for this compound. There are a lot of research that each of that research has a different challenge and different problem, because I can say most of them at high pressure wasn't really precise data. So I mentioned that the beta phase can also obtained by Robertson at the around, I don't know, 50 or 60 years ago, and even more, I mean, 1937. So the beta phase of resorcinol can obtain in the two way. The first way was this method by the melting and heating alpha phase more than melting point, which melting in 110 Celsius. And after cooling down, we can obtain beta. And another way which was reported by the high pressure spectroscopy, they compress alpha phase and they believe that it will transfer to the beta at zero 0.5. But in one of my work, which I didn't bring it in this presentation, I try to check this experiment, but we never achieve it. I mean, we compress alpha phase up to 4 gigapascal, and nothing happened actually. But about gamma phase, which you can see it here at 2011, the Kichanov group, they compress beta and they claim that beta will transfer to gamma at the around 5 gigapascal, but they only report some unit cell parameter without any structure. And more interesting structure was epsilon, which it was reported by the Bertkan group at the 2016. And what they did, actually, they are not high pressure researcher. They tried to mix resorcinol with tartaric acid, and after melting, they got the powder. So they did powder diffraction, and by the data from powder diffraction and dynamic simulation and some computational works, they predict that this structure in this powder could be epsilon. And in same actually a paper and report, they also predict that also resorcinol it's possible to have this space group P21. So according to the literature, I draw the phase diagram of resorcinol. What was actually our plan? So I started work on the resorcinol in Poznan, and in all experiment I use mirror bassets because and also the gasket which I used it was a steel gasket foil, and all experiment also was done in the with the in-house diffractometer. But in our lab, we have a 3 diffractometer, but this one actually is a really old one. I think, as you know, Iskuma is really old company for it. And what was our plan? Okay, before starting about our plan, I want to also mention that in our group also for the software, we use the Chris Alice software, which is for diffractometer, and also we use the Shelix and Olex package for solving a structure. And at the beginning, my plan was, I want to just remove this, okay. At the beginning, the plan was this, that I wanted to check, first of all that experiment, which it was in the literature. And also for this, I make a plan to check resorcinol in different solutions with different concentration. So at the first experiment, I did isothermal of crystallization in the water solution. And at the 0.8 gigapascal, I obtained the monohydrate resorcinol. You can see here the crystal, which is really high quality. But when I increase the pressure, as you know, we use water, so we had some limit. We couldn't go to very high pressure. So when I increased the pressure, and after measurement, I couldn't solve the structure. And we noticed on the surface of crystal, it was a lot of tiny structure, which it was similar passivation actually. And so what's happened? So at the beginning, I thought it's possible to be water because it's near the freezing point of water. But when I check it several times, uh, uh, something is wrong here. Okay, now it's okay.
We're not seeing this.
Could you see?
No, not
Okay.
yet. Can you try it again?
Something is wrong. This meeting is very okay. Got it. Screen. So can you see it now?
Yes, that works. Thanks. Mhm.
Okay. So in the another experiment also is happened, because actually in all my experiment I always try it several times to be sure the result is correct, or that pressure we report is a real correct pressure. As you know, we have in our work a lot of errors, so we by the repeat experiment we can give and write correct report. So in the second one, again, I try to work on this, to notice what is happened, because only I had the one measurement from the monohydrate. And as you know, in the isothermal crystallization, by playing pressure, increasing or decrease the pressure, it is possible we be able to grow one of these tiny crystals. So I work on it and I decrease the pressure, and at 0.55 gigapascal, very tiny crystal start to grow. At the same time that the monohydrate resorcinol was dissolving. And at the end, I was able to obtain the new ratio of the hydride of resorcinol, which we check it in literature and we call it duo-3 to resorcinol, duo-3 to hydride actually. And in this case, in this crystal, I also step by step increase the pressure, and I collect the data till 0.93 gigapascal. So till this step, I had only 1 point measurement from the monohydrate, and actually we was sure that monohydrate is only stable in this point, and before and after this pressure we have a duo-3-2. And so we check the structure. You can see here that it was also interesting that duo-3-2 has a disorder in its in the structure, with it's not match with the general rule that high pressure can eliminate the disorder. So what was the reason? When we check the intermolecular interaction and bonding, we notice one of the bond, which you can see it here, is much longer than the normal hydrogen bond. It was near 3 angstrom. So in fact, in this part of the project, we noticed that the hydrogen bond is the main factor to destabilizing the monohydrate phase. So I continue my experiment by different concentration and different solution. And as you can see here, in second part where with working with the water, I decrease in this step the concentration. And after decreasing concentration and continuous experiment, at the 0.25 gigapascal, I obtained the epsilon resorcinol. And this epsilon resorcinol was exactly same compound and same structure and polymorph with that literature which they mixed it by the tartaric acid, and they obtained it by the simulation and computational work. And when I check it also with monohydrate, with the methanol and water, again I obtained the epsilon. And in this case, I increase pressure and I collect data near 1 gigapascal for epsilon. But my challenge about epsilon was that why I couldn't recover this crystal, because they had it at the ambient condition. So if they have it, so if they obtain it, also I should be able to obtain it. And so I try with different solution, and also finally I found another new phase of resorcinol, which is I have never reported. But in this step, we were looking for the reasons that, because this experiment also I tried to do it each of them at least 7 times to be sure the epsilon is not ambient condition phase. But what was the reason that they got it and I couldn't get this form? You can see here also the different parameter of resorcinol and zeta, which was a new phase. But this point, which is ambient condition, I added from the literature. I mean, from that powder refraction. So I update the phase diagram of resorcinol with all our data and achievement. But we try to figure out what's happened and why we cannot obtain it. In this step, we were sure actually that epsilon is high pressure phase, is not ambient condition phase. So we noticed that the tartaric acid will play same role, similar the external pressure, which we have it in diamond angle cell. And we also try to make a model that proves it that this pressure is at least 0.2 gigapascal, because according to our experiment, we were sure that epsilon cannot obtain below 0.2 gigapascal. And we make a model and some formula for it. You can see that the doping pressure, which is PD, we call it PD, is related to the bulk modulus, which is reverse of the volume compressibility of the host compound, which in this case is resorcinol, and also is connected to the and related to the molar ratio. We choose the C here because also it means the concentration. So this molar ratio actually is the percent of our dopant in the structure. So we make also the formula. Here is n plus 1 because and the I mean cubic, because it's in 3 dimension, and we are thinking in 3 dimension, which the dopant can affect on the unit cell. So, for example, if we have a 3 host, which is between 2 dopant, it means the percentage of dopant is 1.2%. So if we have only 1 host between 2 dopants, so the percentage could be around 14%. So in this step, we was looking for another thing to trying to match our equation with experiment and with another result. And we try to repeat the experiment. So I mix tartaric acid with the resorcinol in different percentage, for example, 5, 15, and 25, because also they use different percentage. So when we check it, how they did it actually experiment, they mix these 2 compounds, dopant and host, and they melt it. And after that, after cooling down, they did powder diffraction. And by checking the powder diffraction, they noticed what is the phase. So actually, we after that, we also check it, and it was the same result. Why I add here the milling, because as you know, in pharmaceutical industry, for making tablet, they have to use milling. And we know it that many drug and compound in this step will transfer to another phase. So just for checking, I also check the tartaric acid and the resorcinol, the mix of each of them by the milling without any heating to check it will transfer to epsilon or no, which it was alpha after checking by powder diffraction. Another important thing which I should mention it here, that the volume of dopant, according our idea and formula, the molecular volume is really important, but the more important volume is van der Waals volume, because van der Waals volume, it means the real size of the molecule, which it will, let's say, and let's imagine, penetrate in the unit cell. And you can see here, which van der Waals volume, actually, I calculated with the one software in our group, which Professor Katrusiak made it. And it's not difficult to calculate it, but we did it with software. It was much faster. You can see the van der Waals volume of tartaric acid is slightly bigger than resorcinol, but not too much. So it's possible that the tartaric acid actually be in, dope in the structure and generate some internal pressure. So, but till this step, the data wasn't enough for us, because we need also another confirmation to make this model, this method more general. So for this, we also check several another organic compound, which they all of them are the imidazole, from imidazole family, and for all of them also the high pressure polymorph was discovered before. Actually, I think 3 of them in our lab. So we knew the really precise data of them, and we knew how is their behavior in high pressure. And in the next step, what we did, I tried to do the powder diffraction. So you can see here the pattern of the resorcinol for different ways, which I, of course, generated from the mercury, because I had all of them is from the single crystal data. And you can see how epsilon is really different. And I use from this peak or this 3 peak for finding resorcinol in my powder diffraction data after mixing with the dopant. So you can see here, for example, in 15%, how it's really clear that we have a epsilon. And also by the intensity of peak, I calculate the percentage of the epsilon in each sample. But also it's important to mention it here that we knew when we hit the resorcinol, alpha resorcinol, after that, it's transferred to beta. So in all of this sample, in case of resorcinol, if we have a epsilon, so also we will have some percentage of the beta phase. So in this case, we only have a beta and epsilon. In next step, we wanted to be sure also that is it effect of tartaric acid or no? It's only by dopant and doping pressure. So if it's doping pressure, it shouldn't be connected of the tartaric acid. I mean itself, yeah. So we try with the benzoimidazole or dimethylbenzoimidazole, which here I bring the dimethylbenzoimidazole, which again we mix it with the resorcinol. And we got also the epsilon phase, and you can see how it's clear, how we have a peak of the epsilon resorcinol in this case. Another interesting thing that in all my data, in case of resorcinol or in case of resorcinol or imidazole family, 15% dopant was really good ratio, and I got a high pressure phase in 15% with high percentage of this polymorph. And you can see here also in case of benzoimidazole, which I mix it with the dimethyl benzoimidazole, which is slightly bigger, the van der Waals volume. And again, I got the beta phase of the benzoimidazole. So at the end, we wanted to check the doping pressure, and we wanted to make some summarize about it, that this formula, this equation also its work, and to check everything here. And I bring here some of them, the best data actually. And you can see 15%, which here the molar ratio, I calculate by the amount of that sample which I use, which it was around 4 gram of resorcinol. And then after that, we calculate the doping pressure. You can see by this result, the doping pressure is 0.5 gigapascal. And as you know, the epsilon is stable in this pressure. So we got really a high percent of the epsilon. But in another case, for example, we at the doping pressure, which was near 1 gigapascal, the percent of epsilon was really low. So I believe that because in this area of pressure, the zeta phase of resorcinol is more stable. But the problem was we couldn't recognize it because we had the beta and most of peak in the beta, and zeta was in the same, more or less same position. So it wasn't easy to recognize it. And in another phase about imidazole family, you can see that, for example, dimethyl benzoimidazole, which can transfer to beta phase at 0.26 gigapascal, I bring it here, that when I use 5% of dopant, it generates only 0.1 gigapascal, which wasn't really enough for stabilize the high pressure phase. And as a conclusion, we saw that how different solution and different concentration can affect on the result, and how we generate by playing with these two parameters many different phases of the resorcinol. And also we found by resorcinol and all these experiments more or less general method and equation for doping and stabilize high pressure polymorph. But I should say here that this equation still need to work more and expand in the all area of compound, because for example, how we can put the effect of temperature in this general method model, or what will happen about intermolecular interaction in this case. And also, still, we couldn't use this model for the inorganic compound because, of course, the condition is completely different. And thank you so much for your attention.
Thank you very much, Fatima. Very interesting work. Are there questions or comments from the audience? Just unmute yourself or use the chat box.
So Fatima, I have a question regarding the regarding this crystallization, single crystal practice that you are doing. So you managed to make grow these single crystals inside of the, without any pressure medium, correct?
No, we can use it, we can do it, but in my case, I use with liquid, for example, water or methanol, ethanol. I use the saturated solution. Yeah.
So you basically put the powder of material inside of a liquid, and then you basically heat and pressure and depressurize to
Yeah,
see starting nucleation, right?
exactly. Yeah.
Okay.
So we can do isothermal or without any temperature, or isochoric. For example, I increase the pressure, for example, in 0.5, and then by playing with the temperature, I try to grow the crystal.
Okay. And does it affect basically the choice of the pressure medium? Would it affect the outcome? Like what kind of what phase basically your crystal grows? Because
Yeah,
this is a pretty unique method that you guys are using.
Yeah, it really will affect, because you can see how when I use methanol and water, I got epsilon. But when I use methanol, ethanol, water, I got zeta. So for sure it will affect. So in one of my project also we thought about it. We should find a general method, but it's not really easy, because in some case also the medium pressure, PTM, let's say, it will do the co-crystal, for example, similar generate solvates compound. So it's not really easy as a chemistry to predict it. Yeah, this is a problem. Yeah.
Okay. And have you ever used something like nitrogen or that you can liquefy and use it as pressure medium?
Not in Poznan, no.
Okay.
But we try to do the pure compound, only pure, not. For example, if the compound is liquid, we can do it. It's much easier. But also, I try in case of resorcinol, only powder. So I fill the chamber with a powder, and then I melt it and try to make the crystal. But it's much difficult, because it's whole the sample could be one crystal. So it should be so slow. Yeah.
Thank you.
You're welcome.
So following up on that, do you have any evidence for or against the ethanol or the methanol in those solutions going into the crystal structure, not just the water?
In case of resorcinol, is no. I had this case that also I got solvate with methanol, but I never get with the ethanol. Yeah, but only in this with solvate, not similar water or methanol go to inside crystal. But I got similar solvate condition. Yeah, it has some bonding with the resorcinol.
But in the crystal structure refinement, do you see any evidence for some solubility of those organic molecules in the resorcinol crystal, not just the hydrates?
Yeah, we will see it. Yeah, because they are also because resorcinol is really light atom in the resorcinol. Also, they are same with the water or methanol. Yeah, so we will see it really clearly. Yeah.
You would see it clearly. Okay.
Yeah.
Okay. So in the doping studies, is there any prospect for doing single crystal work, not by creating the co-crystals by milling, but by some kind of co-crystallization to make single crystals, and then do refinements to know better where the dopant molecules are in the structure, not just relying on powder diffraction? Is that possible?
Yeah, I think is it possible? We thought about it, but when we try this one, we cannot use pressure transmitting medium. So it should be pure compound, two pure compound in powder style, and then putting in chamber and try to grow the crystal. But the control of this is not really easy. So yeah, I think we can do it. I mean, it's possible to get it.
More questions or comments? maybe one more. You stopped at about 1 GPa, and that's in the pure water system. That's where I6 basically forms from the liquid at near room temperature. So, but when you have resorcinol and other components in the structure, or I mean, in the solution, or if you're using ethanol methanol or ethanol methanol water, you can go higher in pressure. So is there any reason why you stopped at just 1 GPa or 0.9 GPa?
In case of epsilon crystal, when I had the epsilon in the chamber and with water, and I increased the pressure, still even in 1 gigapascal, which was a polycrystal, was covers epsilon, still I found some reflection for epsilon. I mean, I saw there is epsilon, but it was covered by the water, so it wasn't easy to recognize it or solve it. Yeah, but I saw the reflection of the epsilon in 1 gigapascal. Yeah.
But can you go higher? Can you go to 2 GPa? I mean, the cells.
No, we cannot go because we will lose this hydrostatic medium. Yeah, we have a whole crystal, so it's not possible to go higher.
But in ethanol methanol water, you can go higher in pressure and it remains fluid.
Exactly, we can go till 10 gigapascal.
Yeah.
Yeah. Yeah.
Okay, more questions, comments? Okay, well, thank you very much. It's a very interesting study that you're doing, and we look forward to seeing you over here sometime soon.
Yeah. Thank you so much, Professor.
Okay.
Thank you.
All right.
Thank you all.
Thank you all. See you next
Bye.
time.
Thank you. Bye.